Let's continue our discussion. Last time, we derived the volumetric flow rate of a Casson fluid in a cylindrical pipe. Now here we look at the velocity profile. And recall that the velocity profile of a Newtonian fluid in a cylindrical pipe is a parabolic function. So let's recall so that you know you can put the discussion into the context. Recall the velocity profile of a Newtonian fluid in a cylindrical pipe. This is in a pipe, and we have a parabolic. Now let's think about what happened to Casson fluid. What about Casson or Casson fluid? So one important consequence of the Casson fluid is that for tau is less than tau y, less than the yield stress no flow. So let's look again at the viscous shear stress distribution. It's linear in R. So this is the center line. This is the R coordinate. This is the Z coordinate. So tau RZ as a function of R is minus R minus R delta P divided by 2L. So the linear means it must be 0 at the center line, and that means at the center line. So we know that tau RZ at R equal to 0 is 0, which must be less than tau Y. I'll show with my pen. So that means there is no flow at least at R equal to 0. So no flow and depending on how strong the maximum wall shear stress is, the no flow region may extend some significant distance along the central region of the pipe, or maybe it's a small, or maybe it's a large. So in any case, even if the flow is able to move when it's close to the boundary of the pipe, so there is still a region of fluid which wouldn't move along the center line. So this is where we call the plug flow. So here is a blood vessel. The radius is R. And the velocity profile would look like this. So here, They have radius critical. We call this R critical. Here is when R is less than R critical, there's no no fluid relative fluid motion. It looks like more uniform, and you only start to develop a relative fluid motion outside of this region. So this let's see. When R is less than R critical, the velocity of R is a constant we call the plug. So this uniform velocity along the center region is called the plug velocity. And when R is much larger than R critical, you start to develop fluid flow. The V plug means for the fluid along this region from 0 to R critical, it behaves like a solid. Solid. So we are going to derive the velocity profile for the region which is beyond the R critical. And then that equation will also tell us how to find the V plug. So we will still use the constitutive relation. Let's express gamma dot in terms of viscous shear stress. And recall that the tau, we just wrote the letters, put it against R delta P divided by 2L. So we are going to replace this tau in the constitutive relation with this tau as a function of delta P. So this is the constitutive relation. And this is from force balance. If you don't remember this, go back to our lecture that derives the force balance in a cylindrical pipe. And when we work on the Newtonian fluid, the Pasolya profile, we emphasized that we need two pieces of information. One is the constitutive relation, the other is force balance. And we used that to derive the parabolic profile for the Newtonian fluid. Now we are still use these two pieces of information, constitutive relation and force balance. Now we're going to use these to derive the velocity profile of a Casson fluid. So the procedure or the strategy remain exactly the same. The only thing different is the constitutive relation. So we are just going to mix these two equations together. So you can see we are going to replace the tau in the constitutive relation with the force balance result. So what we will get is gamma dot equal to 1 over S squared delta P. So here we have already opened the square extended or expand the square term. So after you expand the square term and then you plug in the force balance relation. This is what you get. Now, by definition, gamma dot is dv dr. So we know that this is negative. Gamma dot is negative for pressure driven hyperflow. And if you look at this equation we just arrived, on the left-hand side, what we need is absolute value of the gamma dot. That means we need something positive. But the gamma dot in terms of dv zdr is negative. So in order to make it positive, we put a negative sign. That's it. That's all we need. Okay. First of all, that is a random plot. Okay, now what we are going to do is we just integrate it. So you can separate the variables. You put a vz to the left-hand side and the dr to the right-hand side. And you integrate it from 0 to r. So just let me just write one more step so that you can see what's going on. Or as a review, if you have forgot about solving differential equations. The separate variable. Now we integrate it from 0 to r. And not from 0 to r, from little r to capital R. The reason we integrate from little r to capital R is because we know the boundary condition at capital R, and then we want to know the velocity at any position little r. So let's rotate this way. So we integrate from little r to capital R. Here we use r prime just because I has already been used as the limit of integration. Now, when you set up the integration limit for velocity, you need to match what happened to the right-hand side. So when r equals to little r, we have any velocity profile as vz. We need to figure out, we don't know what it is, maybe the function. And when r equal to capital R, due to the non-stable boundary condition, we have zero velocity. So you need to match both sides. And then let's give it dv prime since we have already used vc as the limit of integration. Then you know how to integrate this. This is just like a polynomial integration. Although it looks, the right-hand side looks intimidating, but it's just a polynomial in R prime. So you know how to handle this. And you just need to be careful. So verify on your own. You should get vz as a function of R, something look like this, 1 over s squared. So Okay, this is all you need to figure out. You can also you can also replace delta P with tau W if you would like, but you don't have to. So the reason sometimes people replace delta P with tau W, the wall shear stress, is because they can directly compare the magnitude of wall shear stress and the yield stress. And then they can tell, okay, what's the ratio of it, or like is the wall shear stress greater than the yield stress or something like that. So if you want to do that, you need to use tau W equal to minus delta T divided by 2L. And if you do that, you will get the V as the function of R. As you can see, the entire thing in these square brackets are dimensionless. So you can also think about it as some coefficient or some sort of correction term. If that is the velocity profile for Casson fluid in a cylindrical pipe, it looks long, but we need to make sure that this is only valid for R greater than R critical. So this equation is only valid for R critical less or equal to the little r equal to R. So this is in the region that is now not a plug flow region. So this is not plug flow region. Now let's see what happens to the plug flow region. The dynamics flow region. So this is a region which your position is within the distance confined by R critical. So you are at this region. Now let's see, how do we find the R critical? The first question you may ask, yeah, what is this? By definition, or not by definition, well, but by the physical process, the R critical is the place where the shear stress happen to be exactly the same as the yield stress. So at R equal to R critical, this happens to equal to tau y. Or you may put absolute sign. So that means R critical equals to capital R multiplied by tau y divided by tau w. If you don't remember what it is, so recall that we had one equation which tells us that, let's recall, from the lecture of force balance, we can also express tau RZ equals to R divided by capital R W. This is from force balance. And now, when your tau RZ is the yield stress, this happens at R equal to R critical. That's why you have this relation. So once you have R critical, you can now solve for the plug velocity, because we have derived the velocity. We have derived this one for any region on the plug flow and then above it. So it is still valid at R equals to critical. So that means the velocity plug is this velocity evaluated at R equals to R critical. If this is not clear to you, you just need to sit down and think about it. And once you sort out the relation between these variables, and then you will be able to see why that's the case. So if you plug in, you just replace R with R critical in this equation, and you can use the result of the wall shear stress. You use the ratio of like R critical divided by R equals to tau Y divided by tau W, this relation. So you can get the V plug equals to R tau W divided by 2S squared. So use the ratio of tau Y tau W. So here, we just replace R critical divided by capital R with tau Y divided by tau W with the absolute sign. So you can further simplify this to get something after some simplification. Also verify on your own. After some simplification, you will get V plug equals to R W divided by 2S squared 1 minus 1/3 tau Y divided by tau W squared plus 3 tau Y tau W minus 8 divided by 3 tau W. Okay, this is the plug velocity. So this is valid for R less than are critical. And if R is larger than R critical, then you would use this sequence. This is valid. Or R larger than R critical. Oh wait, my pen isn't working out today. Okay, so this is our derivation of the velocity profile of a Casson fluid. Now let me leave an exercise for you. Problem. A Casson fluid flow in a cylindrical vessel with radius 1.5 millimeter. So a Casson fluid flow in a cylindrical pipe of radius 1.5 millimeter. The wall shear stress is 6 millipascal. Stress is 6 millipascal. If the yield stress is 4 millipascal, then find the critical radius beyond which shear occurs. Find the critical radius critical shear occurs. And my suddenly works. Let me rewrite some of this so that it looks a little bit better. So, oh, okay, hopefully the rest of it is readable. It's cylindrical. Sorry, my pen sometimes doesn't work. Beautiful. So beyond it also some of these so that it's clear for its value. So this thing vertical and then this was okay. Hopefully this help you read it. All right, that's the end of this lecture.